I'm Jonathan Sheaffer. I'll be speaking about how to render a realistic binaural auralization using spherical microphone arrays. I'm working at Ben-Gurion University together with David Alon, who's a PhD student at the lab, and Boaz Raffaeli, which most of you probably know, who's the principal investigator. I understand that so less than 4 integrals is considered no equation, so I can say that my presentation has no equations. The first part of my talk will be a little bit along the lines of a tutorial talk on how can we take a recording from a spherical microphone array and turn that into a binaural signals. So I'll speak a little bit about how to do this process macroscopically. I'll talk about order-limited binaural signals and the constraints that we have in bandwidth and spatial resolution. And I will then define the current challenges that we have when trying to render such binaural signals. I will then, if we have time, talk about some recently proposed solutions, including robust plane wave decomposition, spatial alias cancelling algorithms, and temporally mixed order representations. So we have the sound field. It can be a measured sound field, it can be a simulated sound field, and obviously if it's a simulated sound field and it's a geometric simulation, we have no problem. We have all the information we need about the sound field. If it's a wave-based simulation, we might want to capture it with some array of sensors, and we have this vector P, which is just the collection of the sound pressures Fourier transformed into the frequency domain at each of these Q sensors. Here's just an eigenmic. So the first thing that we want to do, if we want to make something useful out of this information, is we would like to decompose the sound field into plane waves. So we would like to know where these waves are coming from. So we do this process, which is called a plane wave decomposition. Similar, perhaps, to what Filippo described earlier. We can define this the pressure at each of the sensors as a function of spherical harmonics, radial functions, so these are the spherical bezel functions, and A and M is what we call a plane wave density function. Here everything is in the frequency domain. And it's all written in matrix form, so if you want to approximate this plane wave density function, we just take the pseudo-inverse of our spherical harmonics matrix, and hopefully if everything is nice and well conditioned, it works. I'm going to talk about that in a second. Okay, the next step is, once we know where these plane waves are coming from, we would like to integrate them with a free field HRTF. So we take an HRTF catalog, we transform it into the spherical harmonics domain, and then by performing a summation over convolutions or multiplications in the frequency domain between the different frequencies and the plane waves, we end up with a pressure at the ear. So the pressure at the ear can be very compactly represented in matrix form like this. Unfortunately, it's not that easy. It's not that easy because in the process of decomposing the sound field into plane waves, we have to face a number of challenges. So the first challenge that we face is a lack of robustness. Since we sample the sound field using an array which has a finite radius, in the process of inverting this diagonal matrix of spherical bezel functions, we may have bezel functions that would be close to 0. And this is particularly bothersome at higher orders. So if we look at spherical bezel functions for a rigid sphere, so these are radial portions, radial solutions to the wave equation for a rigid sphere, we can see that as the order goes higher, the magnitude of the function goes lower. So at very high orders, if you want to decompose the sound field at order 30, we'll be essentially dividing or inverting very, very low numbers. So in this sense, we want a very large microphone array, because that would be dependent on the wave number times the radius of the array. The other problem that we have stems from the integration with free field HRTFs. Now, over here you can see a spherical harmonic analysis of an HRTF catalog. This is frequency, and this is just mapped spherical harmonic order and degree. So it's not order 800, it's n squared plus n plus m. But what this shows us is that, and this happens because the morphology of the head somewhat approximates a rigid sphere, is that we have energy at high orders at high frequency. So if we represent our series, we truncate the series, so we say, okay, we don't want these high orders, then the frequencies that are going to suffer the most are high frequencies, because at low frequencies, the bezel, these functions have low energy anyway. And that creates a spectral low-pass effect. So essentially, once we integrate with the HRTFs, if we truncate our series, we will get an artificial low-pass effect with a cutoff frequency equals to NC over 2 pi RH, where RH in this case is the radius of the head. So in this sense, a smaller head is better. So far, if we could have a huge microphone array and a tiny head, we won't have many problems. However, here comes the last part, which is spatial aliasing. So the number of sensors on our array determine the possible spherical harmonics decomposition order, and that really depends on the specific sampling scheme that we use. We can have anywhere between 1.3 to 4 times n plus 1 squared microphones for n spherical harmonics. So obviously, we're limited by that. What happens if we try to decompose our signals at a spherical harmonic order for which we don't have enough sensors? We get spatial aliasing. And the spatial aliasing is just like temporal aliasing. It's artificial waves coming at us from many different directions, and that is strictly dependent on the spatial sampling scheme that we use. So spatial aliasing on its own is not frequency dependent, but since we represent the pressure on the sphere with an angular component as well as a radial component, so the radial component makes everything frequency dependent. And then we have another cutoff frequency due to aliasing, which is n times c over 2 pi Ra, where Ra is the radius of the array again. So we want a large array for low frequencies, a small array for high frequencies, and a very small head. A little bit unpractical, so we have to find other ways to deal with it. Okay, so this is how spatial aliasing looks. Okay, so this is a clean sound field. So this is in the space domain, so we have a nice main lobe at order 4, and this nice back lobe. And if we see it, we look at it as a function of frequency. Just on the horizontal plane, we have this nice single main lobe that spans across the entire frequency range. But if we try to decompose this same array at an inappropriate order, so at order 10, we start getting all these waves coming from different directions, and these begin at the aliasing free limit. So that is KRA equals n. Above that, things become contaminated with spatial aliasing. So just to sum up the first part, we want a large array for low frequencies and a small array for high frequencies. So how can we deal with it? Perhaps if we go back to the noise problem and to the robustness problem, the most straightforward way to address ill-conditioned matrix is by some form of regularization. So if we redefine this problem, instead of saying we're going to take the inverse of the diagonal matrix B, we're going to define some more general matrix C, which is also a diagonal matrix, which does not include these radial functions unprocessed, but it can include many forms of radial functions which will not cause low energy at high spherical harmonic orders at low frequencies. And this has been widely addressed in the literature. There are many forms to do that. Perhaps most noticeably, if we look at robustness of these processes, and on one side we have what we call the plane wave decomposition or modal beamforming, which gives us the best spatial resolution but the worst robustness. And then on the other extreme we have what we call a delay and sum beamforming or maximum white noise gain beamforming, which gives us the best robustness but the worst spherical spatial resolution. And there are some other attempts in the literature to regularize this matrix with respect to some desired SNR or some noise amplification. So, okay, there are some solutions, but a question that has not been asked yet is, okay, how do we optimally regularize this matrix. So how do we choose the best trade-off, which would be frequency dependent eventually? That's this trade-off between spatial resolution and robustness to noise. And this is something that we're attempting to answer now. There's a paper coming up for the next ASA meeting in which we look at the problem from a more psychoacoustically informed place. So we say we do not necessarily need a high spatial resolution at low frequencies for perception. So we're coming up with a formulation that would give us the optimal beamforming weight as a function of frequencies for binaural reproduction. That's a little sneak peek. Okay, moving on to the spectral roll-off, or to the low-pass effect. It's quite easy to predict what this effect would be. So if we can take our HRTF catalog and we can sort of assume a diffuse field, so we don't know where the plane waves are coming from. It's a chicken and egg problem, but we can assume for a second that we are in a diffuse field, and we can construct a transfer function that equalizes a low spherical harmonic representation of an HRTF to that of a higher one. So in terms of spectrum. So, for example, the graph over here is an equalization filter that equalizes order 3 to order 20. The dashed lines are if we approximated the head as a sphere, as a rigid sphere. The solid gray line is based on actual HRTFs. So we can compensate for the lost energy at high frequencies, but we cannot compensate yet for aliasing. So this equalization trick will only account for a narrow portion of the bandwidth, which spans between the cutoff frequency of the head and the cutoff frequency of the array. So if we have a very small head compared to, a large head which is larger compared to the array, then maybe we can get away with it. Above that, we will need to do some further processing. And this equalization, we did some subjective testing. And the interesting thing about this equalization is that it not only improves the perceived timbre, it also improves spatial localization and externalization. And that's related to the fact that we're actually restoring localization cues which are encoded at higher frequencies. So, as we said, we still have the big the elephant in the room, spatial aliasing, which we need to handle. So moving on to that, David, who's a PhD student in the lab, has been working on aliasing cancellation algorithms. Now, the idea is that spatial aliasing is completely predictable. We can construct a matrix, which we call D, which shows us how high orders in mode would alias into low orders. So we can design two spherical harmonics matrices, one at order n, which is what we want, and then one at order n tilde, which is what we want to equalize to or to decompose to. And we can see the aliasing pattern. Now, if we did not have aliasing at all, then we will just have a diagonal matrix of ones. So that's the identity matrix here. All of this information in the process will get aliased down to lower orders. But if we can predict that, we can maybe handle it. We can maybe constrain this problem. So essentially, we are not trying to take a fourth order array and to squeeze a 10th order array out of it. No, we're trying to take a fourth order array and squeeze the bandwidth, the spectral bandwidth of a 10th order array from that without aliasing. So essentially, what we're trying to do is we're trying to clean up this region over here. And we can do that by deciding that what we want, instead of this concatenation of an identity matrix and some garbage over here, we just want a concatenation of an identity matrix and zeros over here. So we can say that this is what we want, this is what we have, and we can find this matrix E, which minimizes the error in the plane wave decomposition results in a least square sense. We can solve that, and then we have what we call the aliasing cancellation matrix, which we can take the aliased signals, multiply that by the aliasing cancellation signals, and cancel out the high frequency aliasing. And this is how it looks like. So this is the ideal example. clean single plane wave throughout the entire spectrum. Then we have the aliased example, and this is the result of applying aliasing cancellation. So it doesn't work perfectly. There's still some aliasing noise here, but most of the garbage here at high frequencies is pretty much cleaned up. So the first question we ask there is, okay, how does that sound? It turns out that at least from a preliminary point of view, it sounds quite good. Based on a Mushra test in which subjects were asked to evaluate how similar were the signals, the aliased signals to the unaliased signals to the ideal signals, we got some very encouraging statistically significant results. So these are the ratings. Everybody rated the ideal as 100, and then the aliased at about 50, and with the aliasing cancellation, it's about 85, 88, which shows a clear perceptual improvement, which was also verified by a statistical test. Okay, where do I stand on time? I have 5 minutes?
Officially supposed to finish 5 minutes ago, but I think you started.
I started 10 minutes ago.
Yeah, go on, give it 5.
Yeah, just 3 more minutes. So, so far, I've looked at signal processing methods to extract a broadband binaural response for a spherical array, but we can also employ some psychoacoustic tricks. So if we look at a very special case in which we're not recording a sound field, we're measuring a single source impulse response, and we can do something interesting. We can decompose our impulse response in time into a direct part and a reverberant part. And then what we can do is what we call a temporally mixed order representation. In ambisonics, it's quite popular to do a spatially mixed order representation. But what a temporally mixed order representation means is that we take the direct part and decompose it at a high order and then all the rest at a lower order. Now, since we a priori know where the source is, we can measure using a low order array, remove the direct sound and just stick a spatial delta over there. So this is how it looks like. So this is a sound field with just a shoebox sound field with a number of reflections, everything decomposed at spherical harmonic 30, and this is only the direct at order 30 and everything else at order 6. Now it turns out that if you evaluate it perceptually, you can gain a lot. So if you look at the control group, okay, so we decompose direct at order 30 and reverberant at some order, then, the control group over here, as we reduce the order, okay, our external perception of externalization reduces, which is what we expect from the literature. But if we play this mixed order trick and we keep the direct order at order 30, then only when everything else is at order 0, the effect collapses. So there are no statistically significant difference, and we get the very much same effects when we study localization error. So the subjective localization test, if we vary the order of the entire impulse response from 30 down to 1, as the order is reduced, the localization error is increased, whereas if we keep the direct component at order 30, we get away with it even down to a simple sound field microphone. So, just to wrap up, we've looked at the current challenges in rendering binaural signals based on spherical array recordings, and we've looked at some possible solutions. Perceptual results are encouraging, so it seems that this is not one of those things that you say the paper absorbs everything, so it's not just a bunch of equations on paper. It actually, the results are actually promising in terms of all of this being applicable. If you'd like, I'll be running a demo of a mixed order spherical harmonics representation, so direct at order 20, reverberant field at order 3, so it's a motion-tracked binaural rendering of a multi-source paradigm, so a sort of a jazz club. So you can feel free to approach me. I'll be around here and have a listen. So with that, I will conclude. Thank you for listening.
Thank you, Chuck.